So our speaker today, as you might have guessed, is Eli Bar from our department. And Eli, yeah. So I don't think Eli needs much introduction, but I'll say a few words. He started in Tel Aviv, where he did his PhD and post in MIT. And then Reed stopped. I don't remember in what university. Notre Dame, yeah, that's right.
That's in the United States.
Notre Dame. Notre Dame. He joined Marginal around 2004, 2005. Yeah, and from since he's been here, and among his many his different prizes, he is also an excellent lecturer and was recognized for this achievement. And I know
today I'm going to spoil it.
Yeah, so we expect nothing less today.
Okay, thank you very much. I'm very happy to see you. Happy Hanukkah. So in the last few years, I've been interested in a branch of mathematics called infinite ergodic theory. I don't know if this is fortunate or unfortunate. And we have shown many applications of this theory. But today I'm going to discuss a particular work that is an example of this broader aspect. And this is the so-called non-normalized Boltzmann-Gibbs statistics. This is how we call it. And this is joint work with David Kessler and the PhD of Erez Avion. So the outline of my talk, I'm going to just remind you basic issues in statistical physics. What is ergodicity? What is Boltzmann-Gibbs statistics in the context of a very simple problem of a single particle problem? And then I'll present these non-normalized states, ensemble and time averages. These non-normalized states in mathematics, they're called infinite measures. And my opinion is that these infinite measures are very important in many physical applications. So in some sense, we're just showing an example of a very general mathematical framework, how to apply it into physics. We're going to show all kinds of thermodynamic relations that apply here that are different than the usual ones. And if I have time, I'll discuss briefly nonlinear maps where the chaos theory breaks down. So let us just remind ourselves what I mean by ergodicity. So let us assume ergodicity in the laboratory. So we have a super simple system. This is a particle, and you have here a spring, and it's all immersed in water, but it can be also a gas. And this system is a bath. It has a temperature T. The interactions between this bead and the environment can be extremely complicated. However, there is certain magic in physics, and that is this bead, if it's small enough, will fluctuate in time. These are thermal fluctuations, and the particle position as a function of time will do something very complicated. This is the time trace of the evolution, X versus T. Now we can do two types of experiments. One of them, you perform an experiment on one single particle, or another option is you prepare many ensembles, many systems like this, and you create some ensemble. You can create average over many systems or along one long trajectory. If you have many particles, you look at them at one long time. So this is a spring. So this is the potential V of X. Then according to Boltzmann-Gibbs, independent of what is the environment, the distribution is simple, exponential of the energy divided by temperature. And here the energy is actually the potential energy, V of X. So I have here this harmonic potential, and then the equilibrium density is a simple Gaussian, as simple as that. Now I can do two things. I can average over time of some observable. For example, the position observable, that is a time average, and I can average over ensembles. And this will give you the same result in the limit of long times, and initial conditions are wiped out here completely because of the interaction of the dust. So if we have a particle, a single particle in a binding force field, so we have some potential independent of time. So the canonical ensemble is simply exponential of the potential over temperature. This will give you the spatial distribution. And then we have here this function Z. This is a normalization. The normalization is also called the partition function of the system, and it's simply the integral over this energy in this case. And the ergodic hypothesis is the following. You have here something, I don't know, there is some observable, O of X, can be many physical observables, which depend on the path. And this is the complicated thing, that these in principle depend on the path. You can do in principle, so this is the function now. So you do an integral over time, you divide by time. And I denote this with an overline, O average. So the bar is the time average, and this is going to be equal to the ensemble average in the limit of long time. The assumption here is that the dynamics has some characteristic time scale. And then the ensemble average is given by this famous Boltzmann average, as you all learned in statistical courses, and this is, of course, all well known. So the main issue that I became interested in these normalized states is that in many cases this Z diverges. This I noticed already. Yes.
Is there something about the locality of O, or O can even be extended out?
So I assumed in the previous transparency that the observable is such that this integral exists. So you can define observables that go like e to the power, let's say for harmonic potential, e to the power x to the power 4, for example, then this thing will not exist and then it's not valid. But these are non-physical observables. So generically for physical observables, this method works, but there are some very remote extensions that no one really cares except me and a few other people. Okay, so this non-normalizable, that is the partition function Z, may diverge, is very common actually. And the first place that I'll give you one example where this is discussed, and this was a paper by Fermi from 1924, that is actually 1 year before Schrödinger equation, but a little bit after Bohr's old quantum theory, right? So Bohr made a big discovery in physics, and that is, of course, the quantum theory. You have an hydrogen atom, you have an electron, you have a proton, and according to Maxwell equation, as you all know, you'll have here some acceleration, and because you have acceleration in classical theory, this electron has to collapse on the proton because it emits light, it loses energies. And then Bohr comes and said, no, you don't have these classical trajectories, so there's no problem. These trajectories are actually quantized, all quantum theory. Then what does Fermi do? He kind of rebukes, at least in my mind, he rebukes Bohr and he said, yes, you are right, but there is a second problem. The other problem is that if you have here in this room, let's say, a hydrogen atom, and assuming it's in thermal equilibrium with some bat, which is all the other part of the universe, let us apply statistical physics to this simple system, a hydrogen atom. And then he does it, maybe you cannot see. You have here R over I squared. I squared is the spectrum of the hydrogen atom in the quantum theory. I is, we call it N. And you can see that this PI, if you sum all these guys, that is, you calculate the partition function of the hydrogen atom, the partition function diverges. And the reason is that the Coulomb potential is flat, asymptotically flat at large distances. Essentially what happens is that the entropy is winning always. And that's why, according to Fermi, or this was well known also in classical physics, the hydrogen atom in this thermal setting is simply unstable. That is the reason, this is how I discovered it, that no one teaches you in statistical physics the hydrogen atom. That is the only course in physics that you do not learn about the hydrogen atom or the Kepler problem, because it simply doesn't work. So we have here an example of a problem. So of course, this is also true for the Kepler problem. So for example, everyone is taught this famous equation of the barometric formula, giving you the density above Earth, which is given by mg, the distance from the Earth over k Boltzmann T in a thermal setting. This is fine. However, it's true provided that the Earth is flat and infinite, because the true Keplerian potential will simply be not normalizable, and in principle everything breaks away. So we see here in one, this is a paradox for theoretician in the sense that the real system is not in equilibrium. The hydrogen atom maybe is in equilibrium, But I'm just pointing out here that there is in very simple potentials, essentially every potential that will go to be asymptotically flat at large distances, you will not have a thermal state, even though intuitively, of course, this formula is correct. And of course, an hydrogen atom that exists here does exist. I mean, there's no doubt about that. So the problem is more with the theory and with how we teach the theory. Yeah, okay. So this concept of a partition function that exists in the theory of glasses by Jean-Philippe Bichot. So if you have a density of states, a usual one, you have a temperature, he described glasses with some disorder Tg, and the density of states itself is exponential. And when you have an exponential density of states, then the partition function diverges when the temperature is low enough. And this, according to a theory, I'm not going into the details of Bichot, describes centered elements of glassy systems. This was investigated in glassy physics a lot. So to solve this issue, there is a standard trick, and that is to introduce some cutoff. For example, the hydrogen atom is not in a Coulomb potential, but it's in some box. I don't know what the box is. There are all kinds of cutoffs in real life. I don't say they do not exist, but in math, and that is infinite ergodic theory, and it was developed by Aronson and these guys. Aronson is a professor at Tel Aviv University. It has a very different approach, and that is you leave the non-normalized states as it is, and you treat it. You don't ignore it. You don't push it aside. You don't throw it away. You say, okay, the partition function, they don't talk about partition function. They talk about the measure, but they use the non-normalized state. And this is what we're going to do today. So to simplify things even more, consider a very conceptually simple experiment. So you have a membrane. This was done by the group of Daniel Schwartz. You have a membrane. This is this plane, and you have one molecule above this membrane. The membrane is attracting the particle with some potential, or it's repelling a short-range interaction. And then in these experiments, you can see the particle moving, and then it can go up inside into the medium, and it can come back, it can go up and come back. And this is the position, this is in nanometers versus time. And we are going to analyze this. I think everyone sees this is more or less the same problem that Fermi had, because the potential is going to be flat. But the issue here is that we have here a single molecule above this surface. So I can follow it. I can analyze its statistics. I want to know how much time it will be close to this guy. What will happen to this, however? Eventually, what you expect, and this is true, it will most likely simply go into the bulk. We will see this soon. But the question is, do you have any concept of thermodynamics in this case? So here is the kind of general hand-waving argument. So let us assume we have this potential, which is asymptotically flat. This is classical dynamics. And the particle is inserted into this potential. And in addition, you have fluctuations and noise because of the environment, thermal environment. And then we look at the trajectory. The trajectory is, of course, very complicated, and it goes in, we'll soon model this with some Langevin dynamics. And then we define two observers. One is the guy in the laboratory, and one is I call him the lazy observer. The lazy observer, he just looks at the system only when it's in some domain, simply because he cannot see more. Actually, most single molecule experiments are like that. They cannot look forever, so they look in some domain. So this guy, what he does, he takes this trajectory and he plots it here. Okay, here it's outside, he throws it away, then you go here, you come back, and then you take this part of the trajectory, you put it here. So of course, the lazy time is much shorter than the laboratory time, okay? But then let us look at this guy, the lazy observable. He has this particle, it comes here, it's like a reflecting wall here, it comes back. So you have here a system, and if you think about it, there's a temperature here, you have a potential. What is this? This is should in the long time limit, should go to some equilibrium. So this guy will going to see some equilibrium, and actually you're going to see exactly the Boltzmann state, even though the partition function is non-existent, because this potential eventually is infinity. And if this guy in this laboratory sees this equilibrium, so also this in the real laboratory should see some aspects of equilibrium, even though the partition function is divergent. That's the kind of hand waving that you will remember later.
I need to know this
The lazy observable is simply once this particle is outside here, you throw the trajectory. So you have here, oh, I'm not seeing it. I go smoke my pipe and then I continue here.
So this works only in 1D.
So, okay, this is a good question. This works better in 1D because the particle actually returns many times. So this is the notion of recurrency. And I will soon discuss what works in 1D and 2D and 3D, but main part of the talk will be on recurrent works. So this will come soon. So, okay, so we understand that even though the potential is not, there's no partition function, still there is some notion maybe of equilibrium. And then we can analyze this, or we can look at this again. So also one simple thing to do is let's do some simulations. And the simulations are very simple. You have here a potential that looks complicated like this. And inside you have a particle interacting with the bath, doing its Langevin dynamics, fluctuating, there's diffusion, there's the force because of this potential. And we let particles go, and then we look at the particle only with inside this domain. So there are many, many particles. Most of them escape to infinity, but you look at them at some time, and then some of them will be here. That's all. And if you look at them and then you plot the histogram of these guys, so you'll see this type of shape. What is this shape? This is just the Boltzmann state, where you have two minima and then you have two maxima here. And this is for a potential that is going to be flat. That is, there's no partition function here, so it's not normalizable. On the other hand, you could do a second thing, and that is you can have here walls, reflecting walls. And then, of course, there is a normalized state, because it's a finite system. And then you all can do the same experiment, and then it's a numerical experiment, I mean, and then you plot the density and it looks the same. And you cannot distinguish between this guy and this guy. So even though the particles are going away, you have here something very similar to thermal equilibrium.
For any temperature?
For any temperature,
you cannot distinguish.
any temperature, any potential, it can be a hump. If it would be a hump here, then the minimum would be here. It's exactly Boltzmann state. Exponential minus Vx over temperature, that's it.
So the difference between the right and the left is only that in the right one, you didn't take into account the escaping particles.
Here right, I start with many, many particles. I wait for a long time. But I take the number of particles to be infinity before the long time. So some of them are still here. And those that are here will give you this distribution. While here, I conserve particles because conservation is the usual philosophy. So you see it's exactly the same. So now we can formalize this a little bit better with the Langevin equation. The Langevin equation is well known from the time of Langevin and Einstein. Okay, so Langevin wrote an equation. This is an overdamp limit. You have a force field. You have a white noise. And what Einstein said is that the diffusion constant is related to temperature and the friction. This is a fluctuation dissipation. So I assume close to thermal equilibrium dynamics. Then you have an equation called the Fokker-Planck equation for the density of particles. This is the probability density, Pt of x. And then you have this Fokker-Planck operator acting on the density. Here you have the temperature. So in illustrations, I'm going to consider, let's say, a Lennard-Jones potential, which is asymptotically flat. And maybe later, if I have time, a logarithmic potential. So how do you analyze this? The first thing you always do in this type of problems, you say, okay, the derivative with respect to time is zero. That's the steady state. That's the usual steady state. So a mathematical solution of the Fokker-Planck equation is simply exponential minus Vx over temperature, over the temperature. This is, you all know what happens usually. This constant here, depending on the potential, well, it exists, then this is 1 over the partition function, the normalization. But in our case, the normalization is not existing. So what is the usual tendency? Well, okay, let's throw this to the trash because it's not normalized and the solution has to be normalized. But that would be actually wrong. But the question is, okay, you have here something which is not normalizable. How is it at all related to the normalized density? Because the density itself has to be normalized, of course. So that's the question that you have here. And the answer is the following. So, okay, before going into the answer, there is a kind of family of potential fields in my mind. Here I plot the, let's say, the harmonic potential. This is a binding potential. It's of course very common. And then of course this constant is going to be just a partition function. Then you have these log potentials that are intermediate, these flat potentials that I'm mainly going to discuss. And then there are many other potentials like unstable potentials, etc. I'm going to claim that for these type of flat potentials, there's a special property of equilibrium, but it's not for all potential. For example, these guys, they'll be a different animal because what Jonathan actually said, because of the non-return, etc. So we go back to the blackboard, we consider the Fokker-Planck equation for asymptotically flat potentials, for example, the Lennard-Jones potential. The force is non-binding. The density close to the minimum of the potential has to decay in time because particles are going to infinity. Then there is a length scale, 2dt. D is the diffusion constant, that's the scale of diffusion. When x is much smaller than this, we can put an ansatz that the density goes like t to some minus alpha exponential times the Boltzmann factor. Why do I know this? Because the Fokker-Planck operator acting on this gives 0. When I take the time derivative of this guy, it gives me minus alpha minus 1. That is a lower order. So that will be a solution. And then we can say, okay, what happens in the large x limit? Well, it has to be just simply diffusion. So this is t to the minus half. And then this alpha is going to be half in this example. So that's it. And then we can create a uniform solution. Actually, in the papers, it's not like this. We solve an eigenfunction expansion and we prove this, but this is hand waving and this is better than the proofs. So what do we have here? Oh, this is the claim. We have here that the density, the normalized density, is simply the Boltzmann factor times x squared over 4 dt. This gives you also the large x limit and the small x limit. And here you have this decay. Now, the trick is the following. Let us look at some x, which is finite, and take the limit of time to infinity. And then this guy will go away. And then what we see from this equation is the following, that this limit, this kind of diffusion part of this thing goes to 1. And then for asymptotically flat potentials, we get a very famous equation in physics. And that is, you take something like the partition function times pt of x and simply the Boltzmann factor. This is the same as usual statistical physics, but then z is simply the norm independent of time. And what is z in this case? It's simply square root of pi dt. But here you have this density, which I call the non-normalized density because it's not normalized. It's independent of the initial states, and all forces in nature are asymptotically flat. So this should describe many things in principle, at least. So the importance of being flat is, let us consider another type of potential, an inverted parabola. Also here in the long-time limit, there's no normalization. We can solve this example. I don't want to go into the details, and we can show that in the limit of long times, if you take the normalized density, and here you multiply it not by t to the half, but by some exponential function, you get something like in the previous one, but this one depends on the initial condition. So here, the initial condition is not forgotten, while in the other examples, it is forgotten. So there's no Boltzmann-Gibbs state here. The initial condition remains here forever because this depends. If you have an unstable field, you start from this side, you're more likely to go to that side or not. So this has to do something with the flatness. Now, in statistical physics, what we do is we always average things. That's the reason why we look at this. And then let us look at some ensemble average. So the ensemble average is always described with respect to the true normalized density. This is just a definition. This is an ensemble average. And then I can take the formula from previous transparency, and I have some OX, some observable, and then I have this Boltzmann factor in the limit of long time, all this, and you need to divide by this Z. So again, this is a famous equation where usually people take here Z independent of time, but it's exactly the same. This equation has one important condition, and that is that this integral exists. The question then in physics is, are the physical observables of interest such that this integral exists or not? And the answer is that many of the physical observables, like energy in this problem, the time you spend in a domain, etc., they are integrable. That is, if you plug here a number, this integral will give you something finite. If you plug here O of x equal 1, this will give you infinity. That's an example of a non-integrable observable. So following the mathematicians, we have classes of observables, either those which are integrable with respect to this non-normalized states or non-integrable. And these two classes have very different behaviors, and I'll talk only about the integrable ones, even though the non-integrables are very interesting. For example, if O is x squared, in our example, this will depend on the tail, the far tail. This will be described by the diffusion because it samples the rare events in, not the rare events, the Gaussian propagation of most of the particles. Okay, so this is an example. We have here a Lennard-Jones potential. So this is like the wall, it's repelling, there is a minima. This minima is not too deep. And we let particles start here and we let them evolve. And then we just multiply the normalized density by this z of t. Z of t is, as I said, going like t to the half. So what do I do here actually? I take a normalized function, I multiply by t to the half. What is the area under this function? It has to be infinity because I'm multiplying by this function that is increasing with time. And then what you see, indeed, you see this peak. What this peak means, it corresponds to this minima. This is the theory, the black line, and the dots are numerical simulation for different times. And this is the shorter time, and as you go longer and longer, this will go to this one. And of course, the area underneath this curve is infinity. That's why the mathematicians call it infinite measure. Still, if I have some observable that, you know, the integral over this thing times the observable will be finite, then this structure of the Boltzmann state will give you the result, whatever it is. So let us now discuss what are the consequences of this in this simple example for statistical physics and thermodynamics. So there are many examples, but I'll discuss three. And one of them is the whole machinery of statistical mechanics can be extended, but for example, the virial theorem. The virial theorem is important in thermodynamics, for example, for all gases. The specific heat of thermal gases, for example, is described by the virial theorem and the related equipartition theorem. So what is it in this case? So in the virial theorem, you are interested in this observable x times the force Fx. And here we can show that if you multiply this by z of t, then you get this answer here. It's proportional to temperature and some other length scale L0. I'll soon define it. This you see, this Fx is integrable. What is the meaning of the average? It's an average over the non-normalized Boltzmann state, because the force goes to zero at large distances, and then this integral exists in our case. Or this we assume it exists. L0, what is L0? Well, it's the second virial coefficient. It's given by this thing. And to see this is trivial. You just use the equation that we had before, and you take the derivative of the potential energy minus 1. You integrate by part. It's two lines of algebra. This is the virial theorem, but it's totally meaningless because we don't explain what is L0. What does it mean? It connects between something and something else, but what is the physics of this L0? So to understand the physics of L0, you need to do something much more than what I did up to now. And that is to solve rigorously the problem with the eigenfunction expansion. This was done actually by David, and understand what is the physical meaning of L0. So we were able to show by the eigenfunction expansion of the Fokker-Planck operator, we went beyond what I was telling you up to now. And we showed the following, that at very large dx, the leading term is simply diffusion because there's no forces. This is trivial. And then there is some corrections, and these corrections are given by L0 times x over 2 dt. And you can see from the units at least that this is correct. And what does this L0 actually mean? It means that there is a force at the origin or close to the origin, and it can either attract the particles back or delay them, or on the contrary, repel them more. So you have this correction term, which is the marvelous thing is that it's independent still of the initial condition. And then if you, for example, look at the mean square displacement, you subtract the asymptotic limit, you get this L0. So what do I mean? You can look at the particles far away, and you can look at this delay caused by this L0, and then you can measure it in principle. And then this L0 is given by the virial theorem. This is how the virial theorem works in this particular, in this setting. So this is example of a virial theorem. So we have here this potential, and you know, here the non-normalized states look something like this. And then you can calculate with it xfx, because you know the non-normalized states. You take this density, you multiply by this observable, you calculate the integral, of course, that you do numerically, because this is a complicated function. And then in the long time limit, you will converge to this thing. Okay, this is one example. But now I want to discuss the time average, because in statistical physics, the time averages and the ensemble averages give you the same thing. But now, what will happen to the time averages? Are they related at all to the ensemble average? Because time is an important factor in this theory. So what we can say is the following. The mean of the time average is obtained from the non-normalized state. So I take some observable, it depends on the xt, and here I have the overbar, that's the time average. And I average this over many, I perform the experiment once, twice, and then I average it many times. And then I can replace the time average, bless you, and the ensemble average. And then this is related to the ensemble average. And then I integrate it over time, because this is the definition of the time average, and divide by time. And then I get that the time average is related to 2 times this ensemble average. So this is like in the usual statistical physics, that there is some relation between the time average and the ensemble average. But here we have this factor 2. What is this factor 2? It's super simple. Here inside, from the z, we have 1 over square root of t. When I integrate that, I'll get this factor 2. So this is doubling effect, and this is simply because of you integrate over time over the z2, and this you have your alpha equal 2. Now, this alpha equal 1 over 2 is just an example in more general context, and I want to explain now what is the physical meaning of this alpha actually. In a very general way, you will have a time average divided by the ensemble is 1 over alpha, and alpha is between 0 and 1. For example, in the log potential or in other things, it's not always this doubling effect. And the meaning of this alpha, I want to explain now more and more, because that is a parameter that controls a lot of the statistics. So for example, you can take this Lennard-Jones potential, you take the time average energy, you divide by the ensemble average, you divide, and as expected in the very long time limit, the ratio goes to 2, because here alpha is equal half. Then you can do other things. For example, entropy external principle. This is not a proof, but this is kind of standard in statistical physics. You take the entropy, which is defined by P log P, which is a kind of commonism, because if you minimize this, it means that all the states are equal. That is the usual microcanonical setting. Then in the canonical setting, you add a constraint, the beta, which is eventually 1 over the temperature with the average. This is all standard. You have the normalization condition, which is another constraint. And here we add only one more constraint, and that is this x squared is going to be 2 dt. When you take the functional derivative of this, you get exactly what I said. So I just added one more constraint, and you get the what you kind of expected. What is the meaning of this constraint? Essentially, this is telling you that the central limit theorem is working at very large distances, because this is why you have x squared. Of course, this is not a proof, but this is just a way to remember this formula. But it's very similar to the external maximum. What we can do with this, for example, is we can take this entropy here, this P log P, and we can relate it to the energy like in usual statistical physics, but now everything depends on time. So the entropy is log Z, that is like the free energy, but Z now depends on time, and then you have the energy divided by time, and you have additional constraints, so you have one more multiplier, and then you see this here. So this is the entropy in such potential. So in the very long time limit, entropy wins and you get a trivial result. This is just due to diffusion. But then there are these corrections. For example, the energy itself, because of the entropy is increasing, but if you have attraction back, then it's increasing less. This EP is described by this non-normalized state. It's a non-normalized observable. You calculate it, and here you see this is the theory, this is the simulation, and in a very long time limit, only this is going to be important. But you see that the theory works well, and then you can say, okay, what is the entropy divided by the average energy? It's at a fixed time. Time is like the box here, because the box is like square root of dt, and then it's simply 1 over t. This is a thermodynamic relation. But now I want to go into what mathematicians know, and that is, what is the distributions of the time average? Before I took a time average and I averaged it over many trajectories. But now let us say you have only one experiment. You take the time average of some observable and I normalize it. So the average of this guy is 1. This guy in the ordinary statistical physics is a delta function distributed in the long time limit. But in infinite ergodic theory, this has some distribution. And this distribution will eventually depend on alpha, and only on alpha. That's the beautiful thing here. So, for example, let us consider this observable. This is a theta function. So this function is 1 if this trajectory is between two xa and xb. These are like in the lazy observer, you have start and end. So in usual statistical mechanics, the total time in this domain, the integral over this, is the Boltzmann factor times the measurement time. So this is called the indicator function, and this indicator function has a sequence. You are 1 when you are inside, you are 0 when you are outside, so you are in, out, 1, 0, 1, 0, 1, 0, and you have tau in, tau out, tau in, tau out. Now, in our problem, the probability density function of the time out decays importantly like a power law. In the diffusion process, this alpha is half. In other problems, it's something else. What is important? Alpha is less than 1. Why is it important? It means that the average time out, that is when you diffuse in the bulk, in our example, the average time there is actually infinity. When the average time is infinity, you immediately understand that usual ergodic theory doesn't work, because when you time average, what does it mean, long time average? Long time average compared to the microscopical scale, but here the microscopical scale itself is infinity, because the average time outside is infinity. So this alpha has to be less than 1. And this alpha, what is its name, or what is its meaning? It's the first return exponent. That is, how long does it take you to return? You have a distribution of times, and this alpha is less than 1, but you do return. That's important. Because you do return, you have some notion of ergodicity. Because alpha is less than 1, it's not usual ergodicity, it's infinite ergodic theory. Okay. So for our example, alpha is equal half, but again, we can play with this alpha by adding, for example, a log potential. Then we look at this, and this is called in mathematics Aronson-Darling-Katz theorem. You have this observable, no matter what is the observable, actually, as long as it's integrable, you have this observable, and the claim, or here it's hand-waving claim, is that this is equal to n over average n. N is the number of visits into the domain that you are looking at. So you are out in, these are the number of ones you have. So the more you visit, the more this O will contribute to you. The issue is that these number of returns can be calculated, and was calculated from a theory of renewal a long time ago, and it's all related, of course, to something called Levy statistics. What is Levy statistics? Just as a remark, Levy statistics is a generalization of the central limit theorem found by Levy at the beginning of the last century. So there are two types of central limit theorems. One is the Gaussian one, where the mean and the variances are finite, and then there is another one when you sum random variables, but the variance, for example, diverges. Here it's slightly more complicated because we are looking at the distribution of n, while the thing that diverges is this time out, the average of this tau out goes away. So this was calculated a long time, this thing, n over n bar, and then this is kind of easy to prove that the PDF of Psi is equal to this thing with this Levy function. Levy replaces Gauss, and okay, it's tabulated in Mathematica. We can plot it. We will soon plot it. And you see here the alpha. The alpha determines these fluctuations. If alpha is equal 1, this would be actually a delta function, like in usual statistical physics. And generally speaking, you have universal fluctuations because while we could prove it rigorously for this, in general mathematics, this is proven actually for something, for any observable. It doesn't matter what is the observable, and that's in that sense, this law is actually universal. And just to go back to the beginning, this is calculated with the infinite density, and this is the fluctuation. So by saying this, we have all the information we have on the fluctuations of the time averages here. So here is an example. This is this energy as a function of time in this Lennard-Jones potential. So what happens here? When the particle is far away from the minima, the energy is 1. So these are these plateau, and once in a while it goes to the steepness of the potential, and then the energy is very high. And of course, so if you just look at this trajectory, it's super complicated structure. I can take the time average of this, and I can repeat it many times, and then I can normalize it by using the formulas that we had before, and we can plot using a computer the probability density function of this normalized time average. And then what you see here is the following. Here I'm changing alpha. I do this with some log potential, it doesn't matter. And this curve here, half a Gaussian actually, is the case alpha equal half when the potential is flat. When the potential is log, you have a tendency to come back, it's more binding. And then when this is for alpha equals 0.8, you get a peak. This peak is to be expected. What will happen when alpha is 1? You'll have here a delta function, which means that the time average is exactly always equal to the ensemble average. The fluctuations here, by the way, are not so big in the sense that the variance of these fluctuations are finite. So as alpha goes to 1 from below, you get here a peak, and that is usual ergodic theory, while in more generality, if the observable is integrable, you get these kind of general fluctuations. How much time do I have? It's a good question.
Yeah, 7 minutes or so.
Okay, so after now I described this, but I described it for an infinite system. Now I want to do very briefly is to say that this is more general, and I'm going to give you another example, but I'll try and be very brief. And this is actually how I started this investigation, and this is from nonlinear dynamics. And the important thing here is we have some type of dynamics. It's not spreading till infinity. It's on a finite size. So, and I'll eventually, if I have time, I'll show you that this is some kind of special nonlinear and driven and dissipative oscillator based on work of Holger Kantz. But I'm going to discuss this map, which is maybe for many of you, it looks a little bit obscure, but this is good because you always start with something simple. So this map is, by the way, very famous. It exists in all textbooks of chaos. It's not something exotic, too exotic. And this map, you have xt plus 1, it's a map x of t. And the important part of the map is what is happening next to this point. This point is called the marginal fixed point, or marginally unstable fixed point. Now you all heard about unstable fixed points, and people will usually teach you about unstable fixed points, but there is also a concept of marginally unstable fixed point, which totally changes the rules. For example, there's no chaos in this map, etc. But what does the particle do? It goes like this. This is the red line, tuck, 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 and then it goes to this part of the map, which is chaotic, and this part of the map injects you back. And then if you go here, you'll be stuck, but you escape very, very slowly. And importantly, here in this vicinity of this part, you have this Z here. This is the nonlinearity of the map. This nonlinearity of the map, I claim, will determine what is alpha exactly. Soon you will see this. And why did we start at all with this problem? Because in physics, there was a big question, because people tell you, okay, there's chaos, Lyapunov exponents are finite. Then there is non-chaos, Lyapunov exponents 0. In some sense, this is misleading because there's many things in between. It's not only exponential spreading, it's also sub-exponential spreading. And here, this is famous map, gives you an example of this sub-exponential spreading. And then we understood that this is related to this infinite density. So the idea here is this is totally deterministic. There's no noise except for the initial condition. We assume, let's say, the initial condition is uniform. And in the vicinity of the unstable fixed point, you have a continuum approximation because the steps there are very small. This A is not so important, so it goes like x to the power z. Now, it's super easy to integrate this equation. And if you start at some initial condition x0 and you reach some boundary B, not so far from the unstable fixed point, then I can calculate the time it takes to go from the initial position x0 to B. Now, what is this initial condition here? This is given by the injection back on the other side of the map. So let us assume that you have some density, which is finite, close to 0. So the particles are injected back. This can be proven from the right of the map to the left of the map. And you have this smooth injection, and then this was done a long time ago, the waiting time PDF of these times close to the unstable fixed point, they decay like power law, like what we have before, but now this alpha depends on Z. So in the previous example, alpha was half because of diffusion, and now alpha depends on the non-linearity of the map. And we again treat the case when alpha is less than 1 or focus mainly on that. That means that when you go close to this unstable fixed point, you stay there for a long time, and you see this here in this trajectory, and then here I'm looking at log of the derivative of the map. That gives you a measure of the Lyapunov exponent of this. This is my observable here. So the idea is that the log of the derivative of the map is proportional to t to the alpha. That is like the number of renewals that we had here, or the number of coming backs. It's kind of similar. And then we define a kind of generalized Lyapunov exponent. So usually Lyapunov exponents along one trajectory, you take the log of the derivative of the map and you divide by time t. But now, because it's infinite ergodic theory, I divide it by t to the alpha. So alpha has several meanings. It's the distribution, the limit distribution of this Aronson-Darling-Katz theorem, the return time, how you normalize. Alpha appears in many different disguises in this theory. But now we can control alpha with a knob, which is a non-linearity of the map. And this guy, we could show a long time ago. Okay, we could show two things. And this is following the mathematicians like Aronson and Sader. They knew this. There is an infinite density. What does it mean in infinite density in this case? You start from a uniform initial condition. And then you take the normalized distribution. You multiply it by t1 minus alpha. Before alpha was half, so I had here t to the half, and now it's 1 minus alpha. And of course, this function is normalized, but if you multiply it by something that is increasing with time, then the area underneath this curve in the long time limit has to be infinity. So this is not normalized state. But still, it goes to something. You see, this is for different times. It goes to something, this line asymptotically, if we could make the experiment longer enough. And this decays like x to the minus 1 over alpha. And this is not integrable at small x. So the area underneath this curve, because of this thing, diverges. So again, now we have observables like this Lyapunov exponent is actually sensitive to what is happening here. It doesn't care about these finite cutoffs. Again, in the long time limit, of course. So we could calculate this generalized Lyapunov exponent. And here this 1 over alpha is like before this multiplication by 2, but now it's alpha. And this is how it behaves as a function of z. As a function of z, up to if z is less, z is it's not a partition function. It's a non-linearity of the map. If you are here, and this was known previously, you get the usual Lyapunov exponent. So people before us then say, okay, here the Lyapunov exponent is 0, you have no chaos. It's true. But if you divide by t to the alpha, you get this curve, and you calculate this, you take the log of the derivative, and in chaos theory, you take the usual measure, the normalized measure, if over here. So this part is simply usual ergodic theory with a finite measure normalizable. Here it's non-normalizable, but the only difference is that you replace this with this non-normalizable function, and this interval exists, and then you get this type of kind of transition in the dynamics, which is related to the diverging of the time scale. And on one hand, you have infinite densities, and the other one normalized densities. And you can also look at the time averages, and these are again, like before, you can control the z. So this is this same distribution as before, but for a very different observable. And this is for alpha equals 0.8, and you get more or less this shape when you look at the fluctuations. That is this Lyapunov exponent over one trajectory divided by the average calculated from the non-normalized state. And if I would change z going into the usual case, this function would correspond to a delta function. So the question is, okay, what is this crazy map? It's just good for the brain, of course, but there are other reasons. So for example, these people, they consider this is potential, but it's not like before. This is a potential that depends on time. So Holger used this as an example of this Barometric dynamics. You have a potential, and importantly, you see here in the middle, it's flat. So it's flat, and the system is also dissipative. So you have a mechanism of injection. So the particle will go here, it can lose energy, but then it can fall on top of this thing if it happens, and it will stay here for very, very long time. How is the energy injected into the system? This is this part of the curve. You have local energy injection. So this simple oscillator, you pump in energy on the left and the right. So it's moving like that. But in the middle, there's no pumping of energy. So it's local pumping of energy, dissipation, and this is the nonlinearity of the map here. Because it's dissipative, it's similar to what happens in the Barometric map. And then you look at trajectories and you see this long stickiness. And if you are interested, you can go to this paper and you consider an infinite density with a simple, well, it's not so simple maybe, but it's a nonlinear oscillator driven and damped. That's what's important. Under certain conditions on the fluctuations that pump in the energy, particles will be stuck here, but it's unstable, like what Management said. And in this example, you have this. Okay, so I'll stop here. I just mentioned briefly that we worked a lot on these log potentials. They are important. I think I don't have time, and maybe you want to have somebody. So, I didn't think about questions. I thought about Sukhanyo. So, okay, so just put you here, just to summarize, we have different types of potential going back to the start. You have these harmonic potentials and other binding potentials where you go to normalized state. Log potential is special. There is a kind of transition depending on the strength of the potential. And then you have these flat potentials. These flat potentials allow you to come back many times. And because you come back many times, you have a notion of ergodicity. You sample many times. That's the whole idea of ergodicity. And that's why these classes are different, for example, from these classes, where you don't come back many times and you don't have exploration. But here you have non-normalized Boltzmann-Gibbs states. Here it's totally normalized. And here things depend on the initial condition. However, there is also here something interesting, some PRL in 2018, which also involved an experiment. If you take this potential and you limit yourself for the very rare particles that go here, they will be more or less Boltzmannian line. So this is a conditioning. This is related to our work also in 3 dimensions, which we discuss here. And here I'll just, okay, I want to point out one more thing, that there's many other directions, like, for example, cold atoms. So I believe, after some years that I've been working on this, that, you know, this notion is kind of quite wide, not only in mathematics, but maybe also in physics. Okay, thank you very much.
Thank you.
The slide where you show comparison of the Lyapunov exponent of this model than one and larger than one. That's smaller than 2,000. Sorry. Is that is that comparison of apples to apples? So in the left side, you have the Lyapunov exponent is the way that two trajectories diverge from each other, right? In the right side, if this is weighted by something, I mean.
Okay, I mean, it is weighted in the sense that we redefine this thing, we divide the 1 over t to the power alpha, and alpha is not equal to 1. If you think about this log of the derivative of some measure of separation, which I think is okay, and you accept this as 1 over t to the alpha, so it's not a usual average, then this is a measure, because what is the derivative of the map? It's simply two particles nearby that kind of separate locally.
And unrelated question. So why the Earth didn't do this?
Oh, for many reasons. One of the reasons is possibly that it's not a thermal system for sure. Second reason, we didn't wait long enough, is global warming. Third reason is we have also impacts coming inside. Fourth reason, I have no clue, it's way too complicated. So there is a question about the interactions among the particles at low densities, how this modifies this thing. So in some of the solutions, let's say of this hydrogen paradox, let's say you have a ground state, an excited state, and you have a temperature. The electronic levels compared to usual temperature is so high that you can treat the hydrogen atom more or less like a two-level system and forget all the other energy states. And then, of course, you are normalized, everything is okay. And this will be valid for some time, but not for infinite amount of time. But on a kind of reasonable time scale, it works. So the answer is it works.
Is there an equivalent story about quantum mechanics and tunneling? Or what you're saying now is that you can, instead of looking at standard thermodynamics from the perspective of equals to infinity, and now you can define some sort of thermodynamics when partition function diverges for finite times, right? And all the tunneling problems, Stark effects are also manifestation of the same story, right? Quantum mechanics, all the definition of spectrum is kind when you take first to infinity, and now you.
I don't know about tunneling. It depends what type of tunneling, but I can say in quantum mechanics, I mean, let's say free particles, there's also something fishy about the normalization there when you have a particle in the box in Fourier space, but this is not so interesting, free particle in quantum mechanics. So I don't know about tunneling. I didn't think about it. So I don't see why they should be related.
It's actually the continuation of this question. So Lennard-Jones potential in quantum mechanics is a finite number of bounding states, right? So the Coulomb potential doesn't, right? This is what is the very
no, this is not the issue. The issue is, first of all, you're correct, of course, but this is not an issue with respect to normalization, because also for the Lennard-Jones potentially, I didn't treat it quantum mechanically, but because you have the continuum spectrum, it's not normalized. V of x goes to a constant. So if you want to treat the Lennard-Jones, if you want to treat this quantum mechanically and you want everything to be normalized, you have to put a particle in a box. And then the continuum spectrum will go to discrete linear box. But I don't believe in boxes. I don't believe they actually exist, or they exist a very long time. Before that, you can have, if the system is big enough, you can have this time dependence that is observed before you reach the boundaries. When the boundaries are there, then you'll go to normal state.
But in sensible, you have to continue, so you're sort of not.
Continuum. No, I mean continuum from the point of view of statistical physics, where you sum exponential of the energy divided by temperature, and you have to sum over all of the energy. That is what you are told. And if you do that, you will always diverge, both classically and quantum mechanically, only because of the continuum. But Fermi didn't do it for the continuum because in the original work of Bohr, he had no continuum, he just had 1 over n squared. Even there it diverges because exponential of 1 over n squared, when you sum till infinity, that will go sum of many ones, and that will be infinity. Yes, but right. So if you were in the old quantum theory and you have a finite number of states, then it will work. But you don't, because you have also the continuum. And by the way, Fermi even didn't know about the degeneracy. So this formula, I found the formula of Fermi, which is wrong because the theory was not yet invented.
Okay, so thanks, Eli, and we're on.
Thank you very much.